Hello, my name is Wang from Mitsubishi Electric Research Laboratories. I am presenting on behalf of the Mitsubishi Electric Privacy Enhancing Technologies, or MEL-PETs, team, about our joint context attack, which won the special award for practical attack in the Red Team track of the LLM Privacy Challenge. In this LLM Privacy Challenge, the goal of the Red Team track is to recover personal identifiable information from fine-tuning data. Some examples of PII are highlighted in red in the figure. For this task, the challenge organizers took a public foundation model, specifically an 8 billion parameter Llama 3.1 LLM from Meta, and they fine-tuned it on a synthetic chat dataset in order to produce the Red Team track's target model for this challenge. In this challenge, the Red Team attackers are given access to the target victim model, and we also have access to the masked fine-tuning data samples, where the PII have been replaced with these tags, highlighted in red. Thus, our task is to recover the masked PII with high attack success rate. By the way, the fine-tuning data was split into two sets. For development, a dev set was provided with the answers available in a separate file, which allows for local evaluation. For the test set, only the masked data is provided, and evaluation was performed by the organizers. The general concept of our attack is that token generation, given the context of partial training samples, will tend to continue by yielding memorized training data. However, a key realization is that the same PII often appears multiple times across a data sample, which gives multiple preceding contexts. For example, in this portion of a data sample, we have the same name1 PII appear twice, which is preceded by two different contexts, highlighted in yellow and blue. The crux of our attack is to leverage these multiple contexts for recovering a single PII. We do this by employing beam search to decode the PII while aggregating next token likelihoods from all contexts. We also enhance our attack performance by suppressing special tokens that should not be in PII strings, and we modified beam scoring to promote generating PII of the correct indicated type. Further, we also realized that the evaluation methodology could essentially allow multiple guesses by just concatenating them together. Our attack finished 4th on the public leaderboard, and we won the special award for practical attack. Our attack is quite efficient, with a complexity similar to beam search, and we operated well under the competition compute budget, using about half of the allowed GPU hours. The core of our attack is essentially beam search, except that we aim to find a single continuation given multiple contexts. Thus, the next token likelihoods are calculated for each context and averaged together. We also modify the next token likelihoods to suppress some specific tokens that probably should not appear in actual PII strings. These include all of the special control and reserve tokens, as well as the assistant token, which should be unlikely in PII strings, but is often generated by the LLM. Further, we suppress two open bracket tokens, including one that has a preceding space, which helps to prevent the generation from simply outputting, for example, literally name1 in brackets instead of an actual name. We also modified the beam scoring in order to promote beam selection and hence generation of PII of the correct type. We did this by adding a score term that corresponds to the log likelihood of the beam belonging to the correct PII class. To determine the PII type scores, we simply use the target model prompted to perform zero-shot text classification. To do this, we take the beam string and paste it into this prompt, which is fed into the model, and then we don't even do full generation, but just look at the next token logits for three specific tokens: name, location, and date. We then take the softmax over these three logits to get likelihoods for these three classes. Note that we only do this for these three specific types of PII. There are dozens of other types of PII in the data, but these three common and easy to understand classes cover the vast majority of the cases. We found that adding this log likelihood of the correct class helps to promote generating PII strings of the correct type. So here are the attack success rates for our attack. The format checker code provided by the contest organizers suggested that testing evaluation may allow multiple guesses, as it seems to simply truncate the submissions to 100 characters, convert everything to lowercase, and check if the target appears as a substring anywhere in that submission. Thus, it seems that we can essentially pack in multiple guesses just by concatenating them together for the submission. For the test set, we use the strategy of concatenating all of the beams together. For the dev set, we evaluate this all beams strategy while truncating to 100 characters to be similar to what might be done for testing. On the dev set, we also evaluated top beam strategy, which only guesses the single top beam. For the top beam strategy, we found that longer token lengths improved ASR as expected, since it may be better for recovering longer PII. However, for the all beam strategies, it seems that the sweet spot was fewer tokens of about 4, which may have helped to increase beam diversity for multiple guesses. Generally, more beams improve ASR, but there are diminishing returns while the compute costs grow significantly. Our best test set evaluation achieved an ASR of almost 19%, while finishing 4th on the public leaderboard. The contest allowed a compute budget of 3 H100 GPUs for 24 hours, so 72 total H100 hours for attacks like ours that can be trivially parallelized by simply splitting the test batch across multiple GPUs. However, we didn't have any H100s available, and instead we used a mix of A40, L40, and L40S GPUs. Public benchmarks show that the H100 is roughly 2.5 times faster than the L40S. Thus, we estimate that the compute budget is roughly equivalent to 180 L40S hours. Our highest compute attack, which was the 50 beam 4 token case that achieved our highest test ASR, used only 93.1 L40S hours. Thus, we only used about half of the GPU time budget, while also using GPUs that had only 48 gigabytes of memory instead of the 80 gigabyte H100 GPUs. The unsloth library was very helpful to reduce the overall memory usage and inference time for our attack, and ultimately we won the special award for practical attack in this contest. To summarize, our joint context attack employs beam search to find a PII continuation that jointly considers all given contexts. We also mix in several tricks, such as suppressing unlikely tokens that shouldn't appear in PII, promoting generation of the correct PII type by modifying beam scoring, and concatenating together multiple guesses. Our attack could possibly be improved in several ways, such as by somehow leveraging the original foundation model in some sort of reference attack. Also, our attack was inference only, but could possibly be enhanced if the model was further fine-tuned somehow to encourage PII generation. Finally, our code is available publicly online on GitHub, and we'll be happy to answer any questions now. Thank you.